Alright guys, when we last left our intrepid heroes, they were finishing part B of number 3, and probably questioning their choices in life that led them to this particular physics problem, and that's fair. So, on we go to part C, which is asking the question, it says, using energy, calculate the speed of the total mass when it hits the ground. I mentioned this last time, but the reason it says total mass is, I'll remind you from the original problem, that up there flying in the clouds is this giant dragon thing that it's about to run into. Now, it says it makes contact with the peak, and as I mentioned last time, at the very top, we are traveling perfectly horizontally. Now, the reason I tried to do this is that, yes, this is a conservation of momentum problem, but I tried to keep it as simple as possible by making it just a 1D problem. The person is, if I think we calculate it up here at the top on the X, the rocket is going 46.1 meters per second. And a reminder that the mass of the rocket is 2,100 kilograms. And the bird dragon, oh, it's just getting worse every time I try to draw a picture of it. Anyway, is traveling this way at 8 meters per second and has a mass of 400 kilograms. Now we're going to assume that these collide, and yes, that's going to take some distance for a collision. We're going to go ahead and assume that it's just all in one spot, which is not terribly accurate, but yeah, it'll work for our purposes right here. So, conservation of momentum initial equals momentum final, which should be the momentum of rocket initial plus the momentum of dragon initial, and it says basically that they kind of move together as one total mass. It said in the problem that there's going to be a perfectly inelastic collision and they move together as one. So this is just going to be the sum of momentum final. So this is going to be mass of rocket times velocity of rocket initial before the collision plus mass of dragon bird thing times velocity of dragon bird thing initial is equal to the mass total times velocity final. So we're just going to go ahead and divide that underneath here and plug our numbers in. It should be 2,100 kilograms times 46.1 meters per second plus 400 kilograms times, and this is the big thing, negative 8 meters per second. Why? Because the momentum is a vector and moving to the left. And we divide under mass total, which is just 2,100 times 400, or 2,500 kilograms, for a velocity after the collision of 37.4 meters per second to the right, or positive. And that makes sense because obviously the rocket had a lot more momentum, being a lot bigger, and having a lot more velocity to the right. So it would make sense that the whole thing ends up going to the right, but obviously slower as well because it made contact with the dragon thing. Now, it says we're going to use energy to calculate. So in other words, we have an energy of this kind of ball of mass that's going to take off and hit the ground. So let's consider what type of energies that's going to be. We're actually going to do conservation of, actually, I don't need to put the sum up. We don't usually put that with energy. Mechanical energy initial equals mechanical energy final. The initial, of course, being after the collision, and the final being on the ground. So let's think about what types of energies are changing here. Well, we have gravitational is definitely going to change. Let's go ahead and put that on both sides. There's really no elastic stuff that's happening here. And it probably makes sense that kinetic energy is also going to change. We should probably set our 0. Since this is going all the way to the ground, let's go ahead and set that as our 0 potential energy, and that would be with the final there, which would make that 0. Makes sense that it has gravitational initial because it's up here in the air. You'll remember from last time, it's kind of convenient here. The height at the very peak was 127 meters, so that's going to come into play here. Is there a kinetic initial? Well, yeah. It's moving right there after the collision. There's going to be kinetic initial. Should there be kinetic final on the ground? Yeah, also kind of makes sense that when it hits the ground, it should be going. And I would imagine, based on this equation, that it should be going faster because it should have more kinetic final because it doesn't have gravitational anymore, and all that's going to go in. So let's go ahead and fill out our individual equations. Mass times gravity times height initial plus 1/2 mass velocity initial squared equals 1/2 mass velocity final squared. For starters, you might ask, what mass is this? Well, now that it's moving together as one, that would be the 2,500 kilograms, but you will also notice it's in every single term, so it very nicely drops out. We're trying to find this VF, which, just as a gentle reminder, is in fact speed, but if you look at your problem, it is saying we're calculating the speed, not velocity. So unlike problem A, we do not need to go find angle. We'll be good just to get the speed. So to find this, firstly, multiply everything by 2. I'm just going to put a 2 up here, cancel that, and square root the whole thing. So square root 2GHI plus VI squared is equal to VF. Of course, once again, don't be confused by your I's and F's. You got to be careful. This I is after the collision, and this final is when it hits the ground. So this would be 2 times G times what is the height initial after the collision? That's at 127 meters. Plus, what is the velocity at the top initial? Well, that's what we just found. That's that 37.4 meters per second squared. Square root that. And our final answer is, I have 62.4 meters per second. I've said this every time, but on the off chance that you've only watched this particular video, these numbers might not be exactly the same as yours. They might be slightly off due to rounding. So that's how you do part C. I should have probably put part C somewhere in here. This is part C. Yeah. And actually, I'll come back over here so I don't. I already did part B. Hey, look at that. All right. I'll see you in part D, potentially.